So I come to announce the next presentation, which has the title Cryogenic Storage of Liquid Hydrogen, Opportunities and Challenges of Liquid Hydrogen in Heavy-Duty Trucks. And the paper is presented by Dr. Johannes Winklhofer from SAG Innovation GmbH. And I want to introduce him very quickly. He studied automotive engineering in Graz at the FH Joanneum University of Applied Science, then joined the Virtual Vehicle Research GmbH, where he did also his PhD on process simulation of aluminum sheet metal forming at elevated temperatures in 2011, and then started to work at the Salzburger Aluminium Group, SAG, where he did innovative work on casting process, to mention here the semi-solid casting process, reo casting for high volume production. And in 2017, since 2017, he's heading the R&D department at SAG, and responsible for all the strategic and customer-related SAG products. And among those, there is, of course, tanks, diesel tanks, pressure tanks, and the research and development activities also focusing now on cryogenic energy storage system and liquid natural gas and liquid hydrogen. So, Dr. Winklhofer, please, the stage is yours. We're looking forward to your presentation.
Thank you very much, Professor Bischinger, for the kind introduction. First of all, I want to thank the committee for inviting SAG and me to this year's Motor Symposium under special circumstances, but at least live in the studio here in Vienna. It's a pleasure for SAG and me to introduce to you quite a new topic that has gained some momentum in the recent months, and that is cryogenic storage of liquid hydrogen for heavy-duty trucks. So my presentation will be structured as follows. First of all, I want to talk about transport emission regulations. Then I will introduce to you different zero-emission drivetrain technologies for heavy-duty trucks. Then I will talk about the state-of-the-art of liquid hydrogen storage. Then I will introduce to you the currently in development SAG LH2 tank and its technical specifications. I will compare it to other zero-emission energy storage technologies for heavy-duty trucks. And finally, I will draw some conclusions and introduce our company, Salzburger Aluminium Group, to you. So first of all, you are all very much aware of the problem. The transport sector is the only sector to increase its emissions since the 1990s and accounts roughly for 30% of the EU's total anthropogenic CO2 emissions. 72% of these emissions come from road transport, and from that portion, heavy-duty trucks emit 26% of the road traffic CO2 emissions. The EU is aiming for reducing these emissions by 15% compared to 2019 levels until 2025, and by 30% until 2030. To put that into perspective, that almost correlates to every second truck being sold in 2030 needs to be a zero-emission truck. And as development life cycles for trucks is with 7 years rather long, these trucks need to be developed right now with currently available technology. The European Green Deal takes the reduction goals even further, aiming for a 90% reduction until 2050. So that basically means that all road transport needs to be net zero within the next 30 years. So the graph on the left might look familiar to you. It has been presented quite a lot in the last few months and years. It shows different modes of transport depending on weight and the demand for range. On the lower left corner, you can see following the current public discussions, passenger cars where battery electric drivetrains might be the best option for now, whereas battery electric drivetrains are out of reach for ships and aircraft on the upper right corner. Somewhere in between you can see the commercial vehicle segment that is somehow undecided yet. So for light commercial vehicles, battery electric drivetrains might also be an option, but for heavy duty trucks or even trains, that is undecided yet, and this is where fuel cell electric powertrains might play a bigger role. On the right, I tried to correspond the volumetric energy density of the energy storage to the transport mode, and as you can see, the higher the weight and the demand for range is, the higher the volumetric energy density of the fuel needs to be. And that is basically because in the end it needs to be passengers and goods that are transported in order to make a reasonable and viable transport business, and not the energy system. LH2 somehow has a sweet spot in this graph because it is the zero emission technology with the highest volumetric energy density, and I will detail that in a few slides further. So liquid hydrogen storage is not exactly a new topic. Especially BMW together with Linde and Magna Steyr have developed prototypes until 2007. The so-called BMW Hydrogen 7 featured a 12-cylinder internal combustion engine. It could run a dual fuel strategy, running either way on gasoline or on hydrogen. The liquid hydrogen tank, that you can see in the back of the vehicle had a capacity of 9 kilograms, and that enabled a range of up to 200 kilometers in hydrogen mode. The liquid hydrogen tank is based on a thermoflask principle with an inner and outer tank with a high vacuum and a multi-layer insulation in between. The liquid hydrogen is stored at around minus 250 degrees C at a comparatively low pressure of less than 10 bars. The density increase of liquid hydrogen in comparison to atmospheric conditions is by a factor 700, and that is still 30% higher than the volumetric energy density at compressed gaseous hydrogen at 700 bars. As the principle is based on a saturated liquid that is constantly boiling due to the small but inevitable heat introduction, the pressure in the tank constantly increases and needs to be released at some safety level, and that behavior is called boil-off. And thinking of a passenger car going on holidays for like 10 to 14 days, returning to that vehicle where its fuel has basically disappeared and the car is not maneuverable anymore, that was evaluated as not being appropriate for customer use, and that might be one reason why that concept hasn't been further developed for passenger cars. For a commercial vehicle, that is less of a problem, because in order to operate a commercial vehicle on an economical, reasonable and viable basis, it needs to be almost operated on a daily basis. So the SAG LH2 tanks takes the principle one level higher in terms of capacity and size. So the overall capacity of the tank is 40 kilogram liquid hydrogen. The weight of the tank system is 400 kilos without hydrogen. In contrast to high pressure storage, there is no expensive carbon fiber reinforced plastics. The tank basically is entirely made of stainless steel, almost like a Tesla Cybertruck, but round and not squared, if you know what I mean. There is an external heat exchanger that you can see here. that is run through by coolant water that is heating up the cold hydrogen, that is then run through an internal heat exchanger that will warm up and evaporate the liquid hydrogen, thus increasing the pressure in the tank and supplying the fuel cell with gaseous hydrogen. The level sensor is based on a capacitive principle, and the bearings are made from glass fiber reinforced plastic here in the front and in the back in order to reduce heat input and keep the inner tank in place within the outer tank. So taking a closer look at the most pressing issue with liquid gases tanks, and that is the so-called Blowoff behavior that I mentioned before in this diagram. On the y-axis you can see the fill level, and on the x-axis you can see the operating pressure. And in a typical operating point at around 5 bars and 50% fill level, the tank has a hold time of around 8 days. At lower filling levels, there's just a little bit of liquid hydrogen left with low heat capacity, and that's why it's evaporated quite quickly. As well as high fill levels, there's just a small gas space left that is compressed quite quickly, and that's why the pressure needs to be released within a short amount of time. So overall, a hold time of around 2 days should be enough for a heavy-duty truck, because within 2 days it can remain in dormancy over the weekend without releasing any significant amount of hydrogen. So on this slide, I tried to compare 3 different concepts for hydrogen fuel cell electric trucks from 3 different continents. So first of all, there is the Hyundai Accent fuel cell. That vehicle is already running on the road in Switzerland. It features 7 compressed gaseous hydrogen tanks at 350 bars with a total hydrogen capacity of 32 kilograms that enable a range of 400 kilometers. The Hyundai Accent is a so-called rigid truck with a long wheelbase that offers more packaging space in order to incorporate additional components for the fuel cell as well as the energy storage system. Second, there is the Nikola 2. In contrast to the Hyundai, it features 9 compressed gaseous hydrogen tanks at 700 bars. It has a total hydrogen capacity of 60 kilograms that enable a range of 960 kilograms as claimed by Nikola. The Nikola 2 is a North American so-called Class 8 semi-truck that is quite something bigger than its European counterparts, so that also enables more packaging space in order to incorporate energy storage and additional fuel cell components. Last not least, on the right you can see the recently introduced Gen H2 truck by Daimler-Benz. It features 2 LH2 tanks conventionally mounted on both sides of the vehicle with a total capacity of 80 kilograms that enable a range of more than 1,000 kilometers. The Gen H2 truck currently is the only concept for a zero-emission European truck that is compatible with currently available modes of transport like standardized European semi-trailers. And this is where the LH2 concept shines, with high gravimetric as well as volumetric energy density. And yeah, this is where liquid hydrogen storage makes most sense for the moment. Taking a closer look at this comparison on this slide, on the left you can see the energy storage volume necessary for 1,000 kilometers of range, and on the right side you can see the energy storage weight for 1,000 kilometers of range. And within the zero-emission technology, LH2 has the lowest demand for packaging space as well as for weight on the vehicle. For packaging space, especially in comparison to compressed gaseous hydrogen, and in terms of weight, especially in comparison to battery electric vehicle drivetrains. Even if you take into account the additional drivetrain components like the fuel cell, the additional traction battery, as well as the electric motor, there remains some advantage for liquid hydrogen storage, but especially for weight on the vehicle, the significance is important because payload is a major item for transport companies. So the numbers for the batteries are based off anticipated future top-notch lithium-ion batteries, and even in comparison to that, a fuel cell electric vehicle with liquid hydrogen energy storage might be very competitive. The advantage of volumetric energy density of liquid hydrogen especially becomes obvious when we look at hydrogen transport itself. So in comparison to 500 bar gaseous container that you can see in the middle, a liquid trailer can carry up to 4 times more hydrogen, and that would make it a very efficient supply for future hydrogen gas stations. And as this mode of transport is very much volume dependent, the first choice for hauling this liquid trailer would be a liquid hydrogen truck itself as well, because it offers advantages in transport volume. And now I already want to draw some conclusions. So first of all, zero-emission energy storage for heavy-duty trucks is somehow still in a fluent phase. There are some options available, like gaseous hydrogen storage, liquid hydrogen storage, as well as battery electric energy storage. In this regard, LH2 might offer some advantages, and that first and foremost is long range of more than 1,000 kilometers. Fast refueling, that is basically comparable to what we are used with diesel, below 20 minutes. And it offers maximum transport volume as well as payload. There are some challenges remaining. First of all, there is the design complexity of a high vacuum insulated container, especially in comparison to conventional diesel storage solutions. Then, if you want to refuel such a tank, currently there needs to be some venting and backgas at the fuel station. That is not favorable for the moment. And it has to be mentioned, of course, that currently the infrastructure for refueling a liquid hydrogen propelled heavy-duty vehicle is currently non-existent. There are some opportunities. First of all, Daimler just recently introduced the so-called subcooled liquid hydrogen concept. It should avoid venting and backgas at the fuel station. And last not least, it has to be mentioned that as soon as there is future large-scale liquid hydrogen production, especially of green hydrogen in other industries like the cement industry, the steel industry, or the fertilizer industry, as soon as liquid hydrogen is available in large quantities, it might make up for a very efficient fuel in order to power heavy-duty transport. So, last not least, I want to introduce to you our company, that is Salzburger Aluminium Group. We are basically a tier 1 supplier for the commercial vehicle, automotive and railway market. The turnover in 2019 was 220 million euros with 1,200 employees. We have production locations in Austria, France, the Netherlands, Slovakia, Spain, Sweden, and Mexico. The product portfolio is as follows, and as Mr. Pischinger already has mentioned in the introduction. So the The first product is fuel tanks, so diesel tanks for heavy-duty trucks. Then, of course, we do cryo tanks, which is LNG, and of course, liquid hydrogen. We do air pressure tanks. We do special tanks for low-volume markets. We do hydraulic tanks, and as already mentioned as well, we do lightweight solutions from aluminum reocasting, especially for the automotive and commercial vehicle market. These are some of our customers that we work with. That amongst them, there are the major heavy-duty truck OEMs, as well as some big players from the automotive industry. Last not least, I want to mention that SAG is not only a production company, we have extensive R&D capabilities. We do concept development for our customers. Of course, we can do CAD design. We do virtual testing and simulation. We do prototype production, can do physical testing ourselves, or produce prototypes and hand them over to our customers for their internal testing strategies. So that is the end of my presentation. Thank you very much for your attention, and I would be very pleased to answer your questions, either way live in the studio or in the Q&A online section. Thank you very much.
Yes, thank you very much, Dr. Winklhofer, for this very nice presentation on the technologies on liquid hydrogen storage. I think there will be many questions. I see already some coming up in the chat room. One is, are there any issues with the embrittlement of the carbon fiber bearings at these low temperatures?
The carbon fiber bearings are not in direct contact with hydrogen, so no, there is no problem with that.
And in general, also not at other locations or areas?
Well, everywhere elsewhere, the hydrogen is just in contact with stainless steel, and the stainless steel that we use is hydrogen-proof.
Very good. That we expected, of course. So now comes, have you considered the cost of a fueling station for liquid hydrogen? How expensive is a fueling spot, including the needed cryo equipment?
Okay, we are a tank supplier, so we do not supply technology for a fueling station. What we estimate is a hydrogen refueling station is more expensive than a diesel refueling station, of course, but it might be less expensive than a fast charging electrical charger for a heavy-duty vehicle.
And maybe adding on to this, what is your prediction on the availability of liquid hydrogen fueling stations?
So as we've heard in some of the presentations within this Vienna Motor Symposium, liquid hydrogen will be available somewhere along the hydrogen value chain. So, and as soon as it is available, it would be comparatively easy to refuel a truck with that, so that you do not have to change the state of the hydrogen itself in gaseous state, for example.
Yeah. And then there is another question here in the chat room. Can you already compare the manufacturing cost of a liquid hydrogen system with those of a 700 bar system?
Yeah, as I pointed out, the liquid hydrogen tank is almost entirely made of stainless steel, and it's not a Type 3 or Type 4 high-pressure vessel that is reinforced with carbon fiber plastics. So what we assume is the investment cost on a truck for a liquid hydrogen energy storage system might be lower than that of a high-pressure system at 700 bars.
Okay, maybe I have a question is on the energy. If you look at the total energy chain, liquid hydrogen, clearly the question is how will it eventually come to Germany or Austria or wherever. and when you compare to pressurized tanks, you have to provide the energy for on the compressor. Have you made some comparisons on the total energy chain?
Yeah, liquefying hydrogen takes some energy, and that energy is higher than if you would compress it at 350 bar. I think it's still a little bit higher than 700 bars, but it's comparable. And as I already pointed out, at some point in the value chain, you might have to liquefy it anyway in order to transport it. And as soon as it's liquefied in large quantities, the efficiency of liquefaction might also be better than pressurizing it.
Okay, now I see. Yeah, then what additional heat flow is required to evaporate sufficient hydrogen during the operation? And is it planned to use the heat exchangers on the vessel, e.g. to cool the power electronics of the vehicle?
So as far as we know, well, we're just supplying the tank. We are not responsible for cooling down any additional equipment. As I showed in the presentation, the internal heat exchanger in general is good enough to evaporate the liquid hydrogen, but there might be strategies when you run a truck that might have to be taken into account, where you need to put in additional heat in order to evaporate enough liquid hydrogen.
How SAG is able to support standardization in components as well as connection with refueling station to enable economy of scales and cost down of components?
So we are very much interested in participating in any kind of standardization process that especially refers to the tank technologies itself, as well as the refueling standards and strategies. So you are very welcome to contact us in this regard.
Then you mentioned heat exchanger. I think that's a little bit similar to what, is there a heat pump? If so, why can it avoid boil-off?
No, there is no heat pump. What's basically happening is warm hydrogen is taken, that is run through the internal heat exchanger, and then will that evaporate the liquid hydrogen, thus increasing the pressure and supplying the fuel cell. So no, there is no additional equipment necessary.
Okay, then there is another question. What happens with the blow-off hydrogen and how much is it?
Well, blow-off, I think it's meant boil-off. There's just a tiny bit. I mentioned it in the presentation. You can basically count on 3% per day. It will have to be run through catalytic conversion and then being released to the atmosphere as water.
Exactly. You don't want to go to the hydrogen to the atmosphere.
No, not that much, and not in a state where it can be ignited. So this is what you have to avoid, of course.
There is a question, what is the percentage of total weight of the tank system that is taken by the heat exchanger? So how much is the heat exchanger in proportion to the total tank system?
Yeah, I mentioned the tank is around 400 kilograms, and I don't have that number in mind, but it's maybe 10 to 20 kilograms. I couldn't recall that by heart.
Yes. Maybe I have a question. There is this liquid organic hydrogen carrier storage system. What do you think about this in comparison to the other systems?
Yeah, we know that there are several concepts for liquid organic hydrogen storage available, but as far as our knowledge is going, none of them is currently as far as you could build up a prototype truck with them. So usually they need some amount of heat input in order to extract the hydrogen, and I'm not aware of any strategy on where to get that energy and heat from on a heavy-duty truck in order to release that hydrogen.
Okay. Then there is maybe the final question, since the time is running out from Mr. Krachler von Magna. Do you see challenges in the supporting pressure, e.g. towards an internal combustion engine?
Yeah, I mentioned that the internal pressure of the tank system is comparatively low, and we know that there are systems like the internal combustion engine or even fuel cells that are asking for higher pressure. And yeah, you could think of a pump that is pressurizing the hydrogen, but most efficient, of course, would be to take the hydrogen as it is supplied from the tank with comparatively low pressure. This is what we suggest and recommend.
Okay, thank you very much, Dr. Winklhofer, for this presentation and also answering the question. I'm a little bit jealous. You're in Vienna in the studio. Hopefully soon I will be able to be in Vienna also again. Thank you very much for presentation, answering the question.